Hi guys, today we're going to be looking at A-level for the mathematics, October-November 2023, paper 3-1. It's a further mechanics paper. So we'll start now. Question 1 is about further momentum. So we have two spheres, A and B, and they have equal radii and masses m and 2m. They were moving at equal speed before the collision, and these are the angles they make to the line of centers. After the collision, the component of velocity a along the line is v. So we can see that the horizontal component of the velocity, of the initial velocity, is u cos theta for b and u cos 60 for a. And because theta is smaller than 60, we know that the horizontal component of b for the initial velocity is larger than the horizontal component of initial velocity of a. So after the collision, a would be moving, the horizontal component of a would be this, would be towards the left instead of towards the right. So we know that this would be v. Oops. This would be v. And obviously there's a vertical component. We don't know what it is yet. And B moves perpendicular to the line of centers. That means this will be the final velocity of B. So sphere A now has twice as much kinetic energy as sphere B. Okay. So for part A, we need to show that this equation is valid. So we can use the momentum. So the initial momentum is mass times the initial speed. For now, we are just considering the momentum along the lines. So the horizontal component of the momentum. Because the vertical momentum doesn't change after the collision. So we just look at the horizontal component. So we have, this is the initial momentum of A plus the initial momentum of B, which is mass times the velocity. But because it's the horizontal component is going to the left, so we need to take it as negative u cos theta. So the final momentum of A is m times negative v because it's going to the left, and for B it travels perpendicularly to the line of centers, so there is no horizontal momentum. So we can cancel the m and we will get half of u minus 2u cos theta equals to negative v, and v would be half u times 4 cos theta minus 1. For part B, we will need to find the value of cos theta. So now we can use the fact that the kinetic energy of A is twice of the kinetic energy of B. So now we will need to find the kinetic energy of A and B separately. So the kinetic energy of A is half times mass times the velocity square. So after the collision, the horizontal component of velocity is v, which we have already found here, and the vertical component is just u sine 60, because the vertical component of velocity doesn't change after the collision. So we have the horizontal component plus the vertical component, which is u sine 60 squared. And we would have 1/4 u squared times 16 cos square theta minus 8 cos theta plus 1 plus 3/4 u squared. And we would get half mu times, mu squared times 4 cos square theta minus 2 cos theta plus 1. So this will be the final kinetic energy of A. And now for the kinetic energy of B, we have half times mass, which is 2m, times the velocity. We can see that it travels perpendicularly to the line of centers. That means there is no horizontal component for the velocity. So we just need to consider this velocity. And like what I said just now, the vertical component doesn't change. So we can just take u sine theta. So u sine theta squared. And this would be mu squared sine squared theta. So the kinetic energy of A is 2 times the kinetic energy of B. So half mu squared times 4 cos squared theta minus 2 cos theta plus 1 equals to 2 mu squared sine squared theta. And we can cancel the mu squared. And now we would get 2 cos squared theta minus cos theta plus half equals to, okay, for sine square we can change it to 1 minus cos square theta. So we would get 4 cos squared theta minus cos theta minus 3/2 equals to 0. And we change it to 8 cos squared theta minus 2 cos theta minus 3 equals to 0. And we can factorize it to get 4 cos theta minus 3 and 2 cos theta plus 1. So the value of cos theta would be either 3/4 or negative 1/2. But we will need to reject this because if cos theta is a negative value, then the angle here, this angle, wouldn't be an acute angle. So we reject negative half, and this would be the final answer. For part C, we need to find the value of E, and we can use the Newton's law of restitution, which is VA minus VB equals to negative E times UA minus UB. Alright, for this one, Same as part A, we will only consider the horizontal component for the velocity. So VA would be this value. So half U times 4 cos theta minus 1 minus VB, the horizontal component for the final velocity of B is 0. So equals to minus E times UA is just U cos 60 and UB would be negative U cos theta. So U cos 60, and because UB is a negative value, we would add U cos theta. Now we can sub the values of cos theta. So cos theta is 3 over 4. So we get half U 3 minus 1 minus 0 equals to negative E half of U plus 3 over 4U. And now we would have, oh sorry, VA should be a negative value. Since, okay, VA is going to the left, so it should be a negative value. I'm so sorry. So we would have negative 1 equals to negative 4 over 5E. We can cancel all the U's. So E would be 4 over 5. Question 2. So we have a ball with mass 2 kg and it's projected vertically downwards with speed 5 meter per second. So this would be the initial speed and the velocity of ball is v and displacement is x. So we need to find an expression for v in terms of t. So we have a ball and this would be the weight, which is 2g, and we have a resistive force with magnitude 0.2 v squared. So we can use this formula. The resultant force is m times a. So resultant force in this case would be 2 times 10, which is the weight, minus 0.2 v squared, which is the resistive force, and m, the mass is 2 kg, and a can be written as dv over dt. So we can change it to 10 minus 0.1 v squared equals to dv over dt. And now we can change this equation to 1 over 10 minus 0.1 v squared dv equals to 1 dt. And now we can take the 10 out. So we have 1 over 100 minus v squared dv equals to 1 dt. And how do we integrate this one? We can look at the formula booklet and this one. We can use this formula. So this is in this form. So the a here, the a is 10 and x is v. So we can surely plug into this. We would get 10 times 1 over 20 ln 10 plus v over 10 minus v. And this would just be t with a constant. Now this would be half ln 10 plus v over 10 minus v equals to t plus c. So now we need to find the constant c, and we know that the initial speed is 5 meters per second. That means when t is 0, v is 5. v equals to 5 when t equals to 0. So we get half ln 10 plus 5 over 10 minus 5 equals to c. c would be half ln 3. So we rewrite the equation. Half ln 10 plus v over 10 minus v equals to t plus half ln 3. And we need to find the expression for v. That means v has to be the subject. So we can change it to half ln 10 plus v over 3 times 10 minus v equals to t, and ln 10 plus v over 3 times 10 minus v equals to 2t. 10 plus v over 3 times 10 minus v is e to the 2t. So 10 plus v equals to e to the 2t, 3e to the 2t times 10 minus v, and we can factorize the v out to get 1 plus 3e to the 2t equals to 30e to the 2t minus 10. So v would be 10 times 3e to the 2t minus 1 over 3e to the 2t plus 1. So this would be our velocity expression. Part B. Deduce what happens to v for large values of t. So v is this, and from here we can't really see what's going to happen when t has a large value. So we're going to change it to 10 times. Okay, what we're going to do here is we're going to divide the upper part by e to the 2t and divide the lower part by e to the 2t as well. So we end up getting 3 minus e to the negative 2t over 3 plus e to the negative 2t. And now we can see when t is approaching infinity, this would be 0 because 1 over e to the 2t, when t is approaching infinity, we have 1 over infinity, right? And 1 over infinity is 0. So we have v is approaching 10 times 3 minus 0 over 3 plus 0. So we have v approaching 10. For question 3, we have a square lamina, and I would use blue color for the length and angle, black for drawing lines, and red color for forces. Okay, first we have square lamina of sides 2a. That means it's a square. And we have weight W, and we have the weight. Weight is from the center of mass. So we can first draw these two diagonals. Oops. We draw these two diagonals to know where exactly the weight should be. So it should be in the middle, coming downwards. This is W. And the string is attached to the midpoint E. That means this is A and this is A. The other end of the string is attached to a fixed point P, and the vertex B of the lamina is in contact with the wall. When there's contact, when the lamina is in contact with the wall, we know that there would be a contact force. Oops. We know that there would be a contact force that is perpendicular to the wall. So let's call the contact force as R. Okay. So the coefficient of friction between the wall and the lamina is half. That means this is the coefficient of friction. We call it mu. Given that the vertex B is about to slip up the wall, find the value of tangent theta. It's about to slip up. That means friction should be going downwards. Let's call it small f. Okay. For now, we can use two methods. One, we consider the forces. Another one, we consider the moment. So let's consider the forces first. So we need to draw all the forces out. We have weight, contact force, and friction. And since there's a string here, we know that there is also a force exerted by the string. We call it big F. So for forces, let's consider it. Let's look at it vertically and horizontally. Sorry. Yes. So for F, the vertical component, okay, the angle here is theta, so this should be theta as well. So the vertical component would be F cos theta, and the horizontal component would be F sine theta. And now we have everything in vertical and horizontal, so we can start writing the equations. For horizontal, we have only sine f sine theta and r. So f sine theta equals to r. And for vertical, we have f cos theta, small f, which is the friction, and weight. So we write it as f cos theta equals to friction plus weight. But we know that the vertex B is about to slip up. So the friction in this case would be maximum friction. And maximum friction is mu r. Mu is the coefficient of friction, so we have F cos theta equals to half r plus the weight, which is W. So this would be our first equation. This would be the second equation. We can sub 1 into 2 so that we wouldn't have so many variables. So we know that r is f sine theta, so we have f cos theta equals to half f sine theta plus W. And this would be our third equation. So now we can consider our moment. So for moment, we need to find the perpendicular distance from the force to the pivot. And we can take point B as our pivot because this is the point where the lamina and the wall are in contact. So when we take B as the pivot, whatever forces that act through the pivot, we don't have to care about them. So the contact force and the friction acts through the pivot, as you can see. So it doesn't assert any moment to the lamina. So now we just have to consider this force, the tension, and the weight. So for tension force, we can see that the perpendicular distance to the pivot is just here. And we know that this is A. So we are done with this part. And now for the weight, this would be the perpendicular distance from the force to the pivot. So we need to find this distance. Okay, so we can see, first we can see that this has distance A, this length is A, because it's just half of the square, right? And since these two sides have the same length, we know that this would be an isosceles triangle. So this should be 45 degrees. Okay? And this is another triangle. It's a right angle triangle. So we know that this is 90 degrees. This is theta. This is 45. And now we need to find this angle. This angle over here. So we can write theta plus 45 plus the angle that we want to find. Let's call it alpha for now. Plus alpha plus 90 is 180. So alpha would be 45 minus theta. So this angle here is 45 minus theta. And how do we find this length? Is that, okay, this is also a right angle triangle. So we can use the Pythagoras theorem to find this length. So a squared plus a squared, square the whole thing, we get sec2a, right? So this length over here is sec2a. And we can see that this is also a right angle triangle. So we can use SOHCAHTOA. And in this case, we would use cos. So cos 45 minus theta is the distance that we want to find over sec2a. So distance would be sec2a cos 45 minus theta. And now we can write it into the equation. So the clockwise moment due to the tension force would be F times A, and the anti-clockwise moment due to the weight would be weight times Z2A cos 45 minus theta, which is the distance that we found just now. Okay? So now we can cancel the A's, and we would get F equals to W times Z2. Okay, we get Z2W. And for cos 45 minus theta, we can use this formula. So we would have cos 45 cos theta plus sin 45 sin theta. Okay? And this would give us 1 over sec2 cos theta plus 1 over sec2 sin theta. And we will end up getting W times cos theta plus sin theta. This would be our fourth equation. So we just sub the fourth equation into the third one, because we already have F as the subject, so it would be much easier. So we have W cos theta plus sin theta times cos theta equals to half W cos theta plus sin theta times sin theta plus W. So we can cancel all the W's, and we get cos squared theta plus sin theta cos theta equals to half sin theta cos theta plus half sin squared theta plus 1. And now we get cos squared theta plus half sin theta cos theta minus half sin squared theta. And for 1, we can write it as cos squared theta plus sin squared theta, right? So when we move it back to the left hand side, we get minus cos squared theta plus sin squared theta equals to 0. So we can cancel these two out, and we will end up getting half sin theta cos theta equals to, minus 3 over 2 sin squared theta equals to 0. And we can factorize the half sin theta out to get cos theta minus 3 sin theta equals to 0. Sin theta equals to 0, and 3 sin theta equals to cos theta. So we reject this because it will give us the answer of theta equals to 0, 180, 360, which is the angle that we don't want. so we would reject them. And from this equation, we can move cos theta to the left hand side and 3 to the right hand side. So we would get sine theta over cos theta equals to 1/3, and this is equals to tangent theta. So tangent theta would be 1/3, and that's it. For question 4, we have a light elastic string with natural length of 8a, so let's call this L, and the modulus of elasticity is 5 mg, so let's call this lambda, and a particle P of mass m is attached to the midpoint of the string. So the ends of the string are attached to points A and B, which are a distance 12a apart on a smooth horizontal table. Smooth horizontal table means there's no friction. So the particle P is released from rest when P is at the midpoint of AB. Let's connect AB. So this would be the midpoint. Let's call it M. It has a speed of cert 80 ag. And now we need to find L in terms of A. Okay, so we can use the energy equation. So we know that the energy initial equals to energy final, right? So initially, we have elastic potential energy at P, and the final, we also have elastic potential energy, but at M with kinetic energy. Why is there still elastic potential energy at M? Because the natural length is 8a, and at M it's stretched to 12a. So it is still in a stretched form. So we can write the elastic potential energy at P equals to the elastic potential energy at M plus the kinetic energy at M. So now we can start writing the subbing in the amount. So this is the modulus of elasticity, 5 mg, times the extension square. So what is the extension? Extension is the final length, which is 2L in this case, minus the initial length, the natural length. So we have 2L minus 8A squared. This is the extension over 2 times the natural length, which is 8A. And for the elastic potential energy at M, we have the same modulus of elasticity, which is 5 mg, times, okay, at point M, the extension would be 12A minus 8A. So we have 4A squared over 2 times 8A. And kinetic energy would be half times mass, which is M, times V squared, which is cert 80 ag squared. So now we can multiply the whole equation by 16a. So we would get 5 mg times 4L squared minus 32AL plus 64A squared equals to 5 mg times 16A squared plus 640 a squared mg. Okay, so now we can cancel off the mg and we would get, oh, and we also can divide the whole equation by 5 just to simplify it a bit. So we would get 4l squared minus 32al plus 64a squared equals to 16a squared plus 128a squared. And now we can simplify it to 4l squared minus 32al minus 80a squared. And finally, we have l squared minus 8al minus 20a squared. Factorize it, we would get l minus 10a and l plus 2a. So L can be 10a and L can be negative 2a. And because L in this case is the length of 1/2 of the string, so it cannot be a negative number. So we will need to reject L equals to 2a, L equals to negative 2a. So this would be our answer. Part B. To find the initial acceleration of P, we can use this equation, which the resultant force is equals to mass times acceleration. So we will need to see which forces are there. We know that there's a tension force here and another one here. And these two forces have the same value because it's the same string and the length here are the same. So let's find for the value of T. So T would be the modulus of elasticity times the extension, and the extension would be 20 because this is 10a and this is 10a as what we found in part A. So the final length is 20 and the natural length is 8. So 20a minus 8a would be the extension divided by the natural length. And we would get 15 over 2 mg. So because the particle is going this way when it's released, so the acceleration is going this way, and we will need to find the force in this component. Okay, let's draw a line here. So to find the force in this direction, we will need to find the angle here. So the force, the resultant force would be 2t cos theta. So we will need to find what cos theta is. And Sokatoa, we know that cos is this length divided by 10a. So what is this length? We know that AM is 6a. So by using Pythagoras theorem, we can find for PM. So PM would be 10a squared minus 6a squared. Square root the whole thing, and this would give us 8a. So PM is now 8a. And cos is just 8a divided by 10a. So we have the resultant force as 2t times cos, which is 8a over 10a. And this would give us 12 mg. And 12 mg is equals to mass times the acceleration. Let's call it big A for now, because 10A is used the other side. So let's just not confuse ourselves. So the acceleration would be 12g. For question 5, we have a particle P and it's projected with speed u meter per second square at an angle theta above the horizontal point from O. And it passes through a point which has a horizontal distance of 3a from O and a vertical distance of 3 over 8a above the horizontal plane. And it's given that tangent theta equals to 1/3. Show that u squared equals to 8ag. So we have a projection like this. And the initial velocity would be u. And the angle of projection is theta. So since they're already given us a point, which is 3a and 3 over 8a, we can use this formula to find for u squared. So y in this case would be the vertical distance and x would be the horizontal distance. So y 3 over 8a equals to x, which is 3a, times tangent theta. Tangent theta is 1 over 3 minus g remains as g. X squared is 3a squared over 2. V is the initial speed of the projection, so it will be u squared. And cos squared theta can be written as secant squared theta for now. So we have negative 5 over 8a equals to negative 9a squared g over 2u squared, and secant theta can be written as tangent squared theta plus 1. And we already know that tangent theta is 1/3, so we can just sub the value in. So we will get 1 over 3 squared plus 1. So we can cancel the a here, and we would get 5 over 8 equals to 5ag over u squared. And u squared would be 8ag. So we are done proving. For part B, a particle Q is projected with speed v at an angle alpha above the horizontal at the instant when P is at its highest point. Particles P and Q both land at the same point on the horizontal plane at the same time. That means we have this projection. When P is here, P is at its highest point where the vertical velocity is equal to 0. Q is at this point being projected at speed v at an angle alpha. So we need to find v in terms of a and g. Since it states that they both land at the same point at the same time, we can now find for the time for p to travel to the top. So we can use the equation of v equals to u plus at. So when p is at its highest, vy would be 0, and uy is u sine theta. Acceleration would be negative g, and the time. So g is equals to u sine theta over g. The t here is the time to reach the top. So from here to here. If you want to find the time to travel the whole path, it's basically, so the time of p to travel the whole thing would be 2 times the time used to travel to the top, because the time to go up equals to the time to go down when it's at the same horizontal level. Alright, so now we can find the horizontal distance traveled by both q and p. So let's call this r. R stands for range in this case. So r is the horizontal velocity, which is u cos theta, times the time to travel, which is 2u sine over g. So we would have 2u squared sine theta cos theta over g. And now we have the horizontal distance, we call it the range. We can find the horizontal component of velocity of q. So the horizontal distance traveled is equals to the horizontal component of velocity q, which is v cos alpha, times the time needed to travel from here to here. And since particle q only starts traveling when p is at its highest, but they both land at the same time, we know that particle q travels twice as fast as p. So it uses half the time of p. So since p is 2u sine over g, the time that q uses would be u sine theta over g. This is half of the time that p uses. So we can cancel off the u here, sine cos. So now we have v, Sorry, the cos here is different. My bad. We can only cancel the u and the sine. So v cos alpha is equals to 2u cos theta, because we can cancel the g as well. And now we can find for the vertical component of the velocity of q. So we can use this formula again. So the vertical component for the final velocity at its highest point here, when q is at its highest point, it will be 0. Initial initial vertical component for the velocity would be v sine alpha. Acceleration would be negative g, and the time would be half of the time it uses to travel the whole path. So it would be u sine theta over 2g. So now v sine alpha is equals to u sine theta over 2. And now we can start finding for v. So v cos theta squared plus v sine alpha squared is equals to 2u cos theta squared plus u sine theta over 2 squared. So we have v squared times cos square alpha plus sine square alpha equals to u squared times 4 cos square theta plus 1 over 4 sine square theta, and cos square alpha plus sine square alpha would be 1. So we are left with v squared on the left hand side, and u squared from what we found in part A is 8ag, so we can sub in this value. And what is cos theta and sine theta? We know that tangent theta, let's say this is theta, tangent theta is 1 over 3. So this would be 1 and this would be 3, right? Because tangent is the opposite divided by the adjacent. So this will be 1 and this will be 3. So what is this length here? So we have 1 squared plus 3 squared, square root the whole thing, and we would get sec 10. So now we have this as sec 10. So what would be our cos? Cos is 3 over sec 10. So 3 over sec 10 squared plus 1 over 4 times sine would be 1 over sec 10. So 1 over sec 10 squared. So the right hand side would now be 29ag. So v would be sec 29ag, because the velocity cannot be a negative value. Sorry, because v is a speed, so speed cannot be a negative value, and we cannot accept negative sec 29ag. Question 6 is about circular measure. So we have a particle P of mass m attached to one end of a light inextensible rod of length 3a. And we have another particle Q attached to the other end of the rod. So we have a rod like this with particle P here and particle Q here. It's smoothly pivoted at a point O where OQ equals to X. So let's say O is here. This would be X and this would be 3a minus X. So we can draw a circle. So it moves in this circle. Alright? At the instant when the rod is vertical, with P above Q, so P is above Q, the particle is moving horizontally with speed U. So P has a speed U. When the rod has turned through an angle of 60 degrees from the vertical, speed of P is 2 theta ag. And the tensions in the two parts of the rod, OQ and OP, have equal magnitudes. So we have another circle, and the rod is now 60 degrees from the vertical. So let's say this is the vertical. So this is P, this is Q. This would be 60 degrees. And P is now having the speed of 2 theta ag. And tensions in the two parts of the rod have same magnitude. That means, let's call it T. So they have the same tension force. Show that the speed of Q when the rod has turned through an angle of 60 degrees from the vertical is 2x over 3a minus x times theta ag. So we know that if a rod is turning with two of the points, this and this, they would have the same angular velocity, which is omega. So knowing that they have the same omega, we can now find for the speed. And omega is equals to velocity over the radius. Omega equals to v over r. So velocity of P after turning through an angle of 60 degrees is 2 theta ag, and its radius, which is this distance, would be 3a minus x. And for Q, the speed is what we want to find, so VQ over the distance here, which is x. So now VQ would be equals to 2x over 3a minus x times theta ag. Part B, we need to find x in terms of A. So now we can consider the forces acting on P and Q. So we know that we need to find the forces in the direction, in this direction and in this direction. So one is directly towards the pivot and another one perpendicular to the circle. So for P, we have tension, as what we stated just now, and we also have weight. Weight would be mg, but we have to find it in these two directions, right? So right. So now we can resolve it in this direction and in this direction. So we know that this angle is 60, and we can know that this is also 60 from the alternative angle thing, right? So this would be 60, and therefore the weight in this direction would be mg cos 60, and this would be mg sine 60. So for Q, we have tension in this direction, and now we have our weight pointing downwards. This is also mg because it states that Q is an identical particle. So now we need to resolve it in this direction and this direction. So okay, we know that this is also 60 degrees and that this is a complementary angle, right? So this would be 60. So this direction would be mg cos 60, and this would be mg sine 60. So now we can start solving the question. For P, wait, let me write it down. For P, we can say that the centripetal force is equal. Centripetal force is always directed towards the center of the circle, right? So we can see that centripetal force is the sum of these two forces. Centripetal force is always the sum of forces pointing towards the circle. Let me put this here maybe. So I can say that the centripetal force for P is tangent plus mg cos 60. So the formula for centripetal force can be Fc equals to mb squared over r. This would be the formula that we are using. So m times the speed, which is 2 sub ag squared over 3a minus x equals to t plus half mg. So t would be 4a mg over 3a minus x minus half mg for p. So for q, this would be our centripetal force. So it would be T minus mg cos 60. So centripetal force is T minus mg cos 60, and mass is m. The velocity, the speed of q is this one. So I can write it like this: 2x over 3a minus x sub ag squared over r, which is x. And this is equals to t minus half mg. So t would be 4mxag over 3a minus x squared plus half mg. And now we have two equations for t, and we can equate them together. So we have 4amg over 3a minus x minus half mg equals to 4mxag over 3a minus x squared plus half mg. So we can cancel all the mg's, and we multiply the whole equation by 3a minus x squared. So now we would have 4a times 3a minus x minus 4ax minus 3a minus x squared equals to 0. So 12a squared minus 4ax minus 4ax minus 9a squared plus 6ax minus x squared equals to 0. So x squared plus 2ax minus 3a squared equals to 0, and x plus 3a x minus a, this would be the factorization of it. So we can find that x equals to negative 3a and x equals to a. But since the x here is the length of part of the rod, so it can't be a negative number, and we would have to reject this. So we found that x is equals to a. For part C, we need to find u in terms of a and g. So from part B, we know that x is equal to a. So now we know that this is actually a, and this would be 2a. So previously we found that the velocity of q, the speed of q is in terms of x, a, and g. So now we can standardize it to only A and G. So the speed of Q would be 2A over 3A minus A times theta AG. So this will be just theta AG. And now we need to find the initial speed of Q. So do remember that we have an equation of V equals to R omega, which V is the speed, R is the radius, and omega is the angular speed. So previously we know that angular speed is the same, and that means the speed only depends on the radius. So now we know that the radius of P is equals to 2 times of the radius of Q. That means the initial speed of P would also be 2 times the initial speed of Q. So the initial speed of Q is just half of the initial speed of P, which is U. And now we can use the energy equation. So all the energy gain should be at the left hand side, and all the energy loss should be at the right hand side, and they should be equal. So we see that for particle P, it's now at a lower level, so the gravitational potential energy is lost. So it loses gravitational potential energy, but it gains kinetic energy. And for Q, because it rises to a higher level, so it gains gravitational potential energy, but loses kinetic energy. So we can write here the kinetic energy of P gain plus the gravitational potential energy of Q gain is equals to the gravitational potential energy of P lost plus the kinetic energy of Q lost. Alright? The total energy are always equal, so the energy gain should be equal to energy loss. And now we can start subbing in the values. So kinetic energy is half mv squared, and to find the kinetic energy gain, we will need to find the difference in the square of the velocities, or the square of the speed. So half times mass times the difference in speed squared. So the final speed of P is 2 theta AG, and we will square it, minus the initial speed, which is U, and we will square it. For the gravitational potential energy of Q gain, we have mgh. So mg, and how do we find for h? C. This is actually the height that it increases. So we need to find this height, and we know that the length here is A, so this would be A cos 60. So the height gain here would just be A minus A cos 60. So A minus A cos 60. And for the gravitational potential energy lost by P, we have mg, and for the height, it's the same concept. We have the height here initially, and it's now at this level. So this is the height that we want to find, and the length here is 2a. So this is 60 degrees. So this length would be 2a cos 60. So the height here would be 2a, sorry, this is 2a. So the height here would just be 2a minus 2a cos 60. So 2a minus 2a cos 60 plus the kinetic energy loss, which is half v squared. We need to find the difference in the square of speed, which the initial speed is half u, and the final speed would be cert ag. So we can start to simplify them. We can cancel all the m, and we would get half times 4ag minus u squared plus g times a minus half a equals to g times 2a minus a plus half times 1/4 of u squared minus ag. So we would get 2ag minus half u squared plus half ag equals to ag plus 1/8 of u squared minus half ag. So 5 over 8 u squared is equals to 2ag. So u squared would be 16 over 5 ag, and u would be 4 over 5 times cert 5 ag.